Well, it is really good to be back here, and really, I'm super honored to be invited to give this presentation. And really, in many ways, this is like an invite to kind of drag you into thinking some things through that I've been struggling with. So this will be kind of a strange arc, and I'm just going to dive right into it. I've been thinking about the challenge we have as scientists studying geohazards, and in my mind, I've started using this analogy of the old parable of the tortoise and the hare. That in this analogy, the tortoise would be wild reality. It would be that slow creep towards disaster of natural systems, and the hare would be us scientists trying to get ahead of that and to win this race. And of course, the parable doesn't end real well in this case, and so I'll apologize right up front that it's going to be some kind of sad parts of this talk. But I'll refer back to this parable a little bit through the course of my talk. And we're here in Cascadia, so I thought I should say something about that. There's actually, you could say, it wouldn't be that surprising if sometime during the course of my talk we experience a magnitude 9 earthquake sitting here. And I should qualify that in that I would be really surprised. I'm a human animal. It would shock me, terrify me. But if I try to think a little bit like a scientist and to try to quantify a little bit, there's this, I think the latest, greatest estimate and quantifying probability is a 12% in 50 years. We can do a little math and come up with 0.00002% chance that it will happen in the next 45 minutes, which isn't a terribly high probability, but it's vastly higher than the chances that we are all annihilated by a meteor, for instance. So, I don't know. Maybe that's quite plausible. We could even take and quantify further and say, well, how much does this matter? And one convenient way to do that in our society is to convert it into money. And I'll be very self-centered here and talk about the impact if I were to die from a magnitude 9 earthquake sometime in the next 45 minutes, assuming I'm a typical American and value my life at $10 million, and assuming there's a 1% chance that should the conditional probability, should this earthquake happen, that I would die. I hope it's actually a lot lower than that, but just to throw it out there. It ends up meaning that, be about 2 cents. So maybe if I bought insurance, I could insure my life for the course of this talk against subduction zone earthquakes for about 2 cents plus whatever, administrative fees that the insurance company charged. So yeah, not too surprising, but fairly affordable. To really understand, I think, hazard mitigation when we're talking about subduction zone earthquakes is really useful to go back to the 1964 Alaska earthquake. This was a really pivotal event, not only for Alaska, but also for the community of people that are trying to understand this hazard. And it had really devastating impacts for some people in Alaska. This is the village of Chiniga after the tsunami, and these funny little arrows are marking the upper limit of inundation. The circle is the school, which is the only remaining building in town. The rest of the town was swept away by the tsunami. One of the survivors described the experience. After a few minutes, I began to hear a loud sound. I couldn't see because I was trapped on the floor, but it must have been the giant tidal wave. When it struck the house, it was as if a bomb blew up. Everything was crashing, rolling, and smashing. And she survived miraculously, but many in this village did not. There were also some really surprising geologic effects of this. There were areas that were uplifted, and it was particularly prominent along the coast where intertidal organisms like barnacles were lifted up by the earthquake and died because they were lifted out of their natural habitat. And so a geologist could go and measure the difference between the uppermost dead barnacle and the uppermost living one and estimate how much the land had uplifted. There were other areas that subsided. This photo is actually taken in my hometown of Seldovia. I grew up there. I live there now. The earthquake happened when it was low tide, so the tsunami that arrived, although it destroyed the harbor, it didn't actually flood on land anywhere, which is really fortunate. The whole town was at that time built on boardwalks. And as I learned it as a kid, as people talked about this event, they said that people didn't even realize that the whole town had subsided until days later when the larger tides, the spring tides came in, and they flooded the whole town. And people also talk about the dramatic sociological impact this had, that there was a very contentious vote about whether to move on land or to jack the town up. They ended up voting to move on land, but it was very divisive, and the scars are, still felt today. And so this pattern of uplift and subsidence caught the attention of a U.S. geologist, George Plafker. And he worked to really map this out across southern Alaska and found this area of uplift and subsidence. And he made the connection from this to an emerging theory at that time, something that was still kind of upending geology as we knew it, the theory of plate tectonics. And this ended up being, it's sort of a key to understand this process of giant earthquakes getting generated in very specific places on the planet and having potentially devastating impacts. So if we look at the largest earthquakes recorded on Earth through the 20th century, these ones that are named, these are all subduction zone earthquakes. You can see Alaska there in 1964. That understanding helped also then look back at the Chile 1960 earthquake and Kamchatka in 1952. People were starting to figure these things out. And it turned out we got really lucky because we had 40 years after that without another one of these events. And we didn't waste that time. Apologies to a certain member of the audience for putting his face on the screen. But people worked hard during these 40 years and actually made a tremendous amount of progress in understanding the nature of this hazard and took many steps in an attempt to prepare for it. Another story, you guys might be familiar with the Cascadia stuff, but you may not be so familiar with the work of Carrie C. and many of the people who worked with them, looking in tropical areas at what he called microatolls, these coral heads that preserved a record of changing relative sea level. And in this case, I'll just kind of talk about it as though it's land level change, although it could be sea level change. And so here's an example of one of these microatolls, a photo that I took. And in the middle, you see a dome of dead coral, so that grew underwater. It was killed when the land uplifted. And then as the land subsided, the coral grew back up around it, forming a ring. That was then killed by another uplift event. And then as the land subsided, again, the coral grew up and formed a new ring. And then about 6 days before I took this photo, it was abruptly uplifted in a magnitude 8.7 earthquake that was you could kind of call it an aftershock anyway, of the larger 9 or 9.1 earthquake in Sumatra. And so this was, in some ways, really useful in order to try to understand geologic records of these events. This is work that was done in Thailand. Kuran Jankiao is the first author on this paper. So you can see at the top, this light layer is a tsunami deposit from 2004. And you can see these other events underneath that one. But it was also a horrific natural disaster. Over 200,000 people died in the hours after this earthquake as the tsunami spread throughout the Indian Ocean, even as people died as far away as Somalia, where the tsunami took something like 9 hours to get there. I was there, it was while I was in grad school. I ended up being really involved with post-tsunami surveys, and I think for me and many of the people with me, we were not thinking of this as, a failure of Geohazard's mitigation. We really saw that opportunity. We were like, okay, we're here and we're doing good work because if we can figure this stuff out, that's going to help protect people's lives. So yeah, okay, we'll add this to the graph. So there's 2004 Sumatra earthquake. And really we can make some excuses for not having necessarily benefited the people of Sumatra, Thailand, Sri Lanka, Somalia, many of the places that were impacted. This area around the Indian Ocean is far from where all the money is for doing the research. It was just, we're working on it. Carrie C was in that area doing work to try to figure these things out. Got unlucky. To really test our mettle as geohazards scientists, we would need to see what happened in a place where we're prepared. Like we are here in Cascadia today, we've been preparing for decades for a subduction zone earthquake. And it turned out we didn't have very long to wait. In 2011, there was a magnitude 9 earthquake in Japan. And this photo shows the tsunami pouring over the seawall that was built to protect the town from tsunamis. So there were a number of impacts from this that were very bad. Tens of thousands of people died, huge amount of infrastructure destruction. Let's add it to our graph here. There was evidence that actually was known before the earthquake that this sort of thing was possible. And it looked back in particular to this 869 earthquake, of which there were historical records in Japan. And one of the consequences of this event was the Fukushima nuclear disaster, which I'm going to kind of assume you guys are pretty familiar with, but it was bad. And I just thought this quote from an article I found online was really revealing, talking about Minoura Sensei. Hiro Hasegawa, a spokesman for the Tokyo Electric Power Company, which owns the plant, says the company was aware of Minoura's research and considering making modifications to protect the plant. We were in the process of considering that, he says, but this accident occurred before that process, or during that process. Paleontologist, also clearly a geologist, but often referred to as, he's also anyway, does other stuff too. Koji Minoura believes his warnings were not taken seriously. I regret it, but no one paid attention to my thesis, he says. Since the tsunami, people have paid attention to Minoura. Bloggers have picked up on his work. The Japanese news media have covered it extensively. Minoura now has the attention of the government and is regularly invited to speak before important groups. Yes, Minoura says, acknowledging the attention, but it's too late. So, that's a very sad story I just told, and am I saying, all right, this entire endeavor is worthless? A bunch of scientists did a bunch of work, and what we came away with was failure. And no, I actually think that's very unfair. And in particular in Japan, although the tsunami did pour over those seawalls, the seawalls reflected a tremendous amount of tsunami energy. They slowed the tsunami down. They reduced the infrastructure damage. The estimates of the loss of life within the inundation area in Japan are vastly lower than in Sumatra. I think that if you go back to kind of an actuarial thought process, if you actually measured the reduced cost of that event as a result of not only building all these walls, but all the other research that's gone on, I think you would find that easily paid for all those seawalls and paid all those scientists' salaries. And so your actuary could say success. And that I find very unsatisfying, though, because I look at these events and it's so clear that we could have done better. You can so easily imagine that we might have done better. And I wanted to point to one really kind of obscure little example of kind of the many, many stories that came out of the 2004 tsunami. Brian McAdoo, Laurie Dengler, and Vasily Titov have this paper about this little village of Langi. And the tsunami in Langi was 10 meters high within 10 minutes of the earthquake. The entire village was completely flattened. No structures survived. However, no one died. And that was because they had a cultural knowledge of these events, and they evacuated. And so, it doesn't really give any credit to the scientists, but I think that's a really interesting example showing that there are success stories out there. I want to talk about one other much more recent example, this eruption that happened last year at Tonga. Island volcano here exploded in mid-January of 2022. That's what it looks like after the explosion. When you have a big explosion in the water, it's exactly the kind of thing you expect to generate a tsunami. Not only the explosion itself, but potentially secondary landslides and such. If we go now take a look at a little piece of the nation of Tonga here, this is before the tsunami, a couple weeks before, and we flip to afterwards. I'm going to flip back again. Now train your eye on some of those buildings in the upper left, and you'll see they all vanish here. The tsunami was about 20 meters high in this place. Incredibly devastating tsunami. However, in all the islands here, there were only 4 people who died. And I'm not saying that those 4 deaths weren't tragedies, but from what I saw in the images of that was a surprisingly good outcome. It really impresses me that it went that well. And I wish I knew everything about what led to that, but from what I can gather, the reason that people were so well prepared is a combination of factors. It wasn't so much traditional knowledge, but there was a lot of conversation going on between the community and scientists who were measuring small tsunamis generated by precursory eruptions, and people were very, very aware. And then when this natural warning, the sound of this explosion sounded like the world was coming apart, people responded to that by fleeing to safe places, and thus most of them survived. However, this is a really unusual event, and we have to dig a little deeper into it and think about one of the best analogs, which is the Krakatoa eruption in 1883. Now, this eruption, similarly, a volcano in the ocean, blew itself to smithereens, created a big tsunami. I won't tell the horrible story of how it went for the people nearby. Needless to say, it was very bad. This explosion generated a pressure wave that was observed. This was early in the era of monitoring air pressure in order to try to understand the weather. And so people were watching all around the world trying to figure out what was going on, and they see this pressure wave go over. And they also noticed in places as far away as the Thames River in England that there were water level variations with this. Now, this phenomenon of volcanic meteotsunami is actually well understood by the 1960s. The physics had been pretty well nailed down. It basically, air pressure, the air pressure plus the water pressure have to balance out. So you end up depressing the water surface a bit if you increase the air pressure over a place. And as this depression propagates, it can actually feed energy into a wave, into a tsunami that propagates as a wave. And it turned out in Tonga, it was kind of a special place, right next to the Tonga Trench, which is very deep. And it turns out that the speed of this pressure wave, it tends to be much faster than tsunami speeds, and so it tends not to put that much energy into the water. But over the Tonga Trench, the tsunami speed is a lot faster, and so you actually had more energy coming from this pressure wave than you would expect almost anywhere in the world. And so there was that first tsunami I've already talked about, the one actually created by the explosion, possibly landslides at the volcano. But there was a second tsunami that was a volcanic meteotsunami, completely separate origin. And I went through and I just dug into the National Tsunami Warning Center, the bulletins that they put out, and the advisories and such. And that's what this figure is showing. We don't need to get into too much detail here. But one detail that I want to point out is this vertical line. That represents the time when they issued an advisory. So long after the eruption starts here, so many hours passed, they issued an advisory. It's well after the first waves arrived in Hawaii. And from what I can gather, they were caught flat-footed. That research from the 1960s was never integrated into their procedures for being prepared for tsunamis. However, good. There's the tortoise rearing its head. The hare gets a little credit here because the United States invested a tremendous amount in keeping this tsunami warning center operating as a 24/7 facility that was nimble enough that when they did see these scary things happening in various places, they got their act together and they issued a warning. And they made predictions, even though they didn't really understand what was going on. They made predictions about when the waves would arrive in various places. Generally, the wave arrived earlier, but the biggest waves all arrived after their prediction. Again, I don't know exactly, we don't have the counterfactual, we don't know how much benefit we got from this, but maybe it was enough to pay the budget of the National Tsunami Warning Center for several years. So, a little good, a little bad here. There's one way in which the tortoise just flat out won, though, and that is in Peru, where they don't have that incredibly expensive facility operating 24/7. And when the tsunami arrived there, they had no idea it was coming, and 2 people died, and there was the worst oil spill in Peruvian history. It impacted a whole series of marine reserves along the coast. Okay, I want to go from there and now come up to Alaska, where I really kind of maybe actually know something about what I'm talking about here. This is Lituya Bay. As Jody pointed out, I named my daughter after Lituya Bay here. We visited there just after she turned 10 a couple of years ago. And if you think you've heard of that before, it's probably because of the 1958 tsunami there. It was a big one. It had some incredible impacts. There were several boats in the bay at the time. It actually was not the first tsunami in Lituya Bay. There actually were at least 2 others. We know those very well, and probably somewhere around 5 total. And it turns out what we know only recently is that the 1900 and the 1936 tsunamis both killed people. They were both deadly tsunamis and killed indigenous people that were there in the bay. These types of tsunamis have some kind of interesting properties, worth maybe just a slight detour into the physics. Essentially, if you run a landslide into water at a speed that is faster than that water can get out of the way, faster than the shallow water wave speed, the natural propagation speed of a tsunami, then basically it slows the landslide down. And if you're slowing the landslide down, that means you're taking energy out of it. That energy has to go somewhere, and where it goes is into the water. And so this builds a bigger tsunami. That energy is limited by how deep the water is. So there's kind of a peak potential for putting energy into the water that is deep enough that it can absorb a lot of energy, but shallow enough that the speed of a shallow water wave is less than the speed of the landslide. And it turns out that in typical fjord depths, you're likely to be somewhere in that ballpark. Like catastrophic landslides go, a number of tens of meters per second on these large scales, and that matters when you're in a few hundred meters water depth. So the event that got me started in this is in a place called Tan Fjord, where the Tyndall Glacier is on Icy Bay, and there was a landslide in 2015. October of 2015, that ran down off the mountain and across, a little bit of it went across the glacier and then down the bottom of the fjord, and it generated a quite large tsunami. So the largest run up there is 193 meters. We can see up here. And even down here, miles down the fjord, it's still breaking 50 meters. Really dramatic tsunami. Flattened forests along the side. Let's see, this line here is the high tide, so this is the normal tidal range. This is a brown bear for scale. And and you can see the trim line. This is really actually a place where it was relatively low impact. Some of those areas where it was 50 meters looked more like this. This is a satellite image showing kind of the situation at the source. So here's the landslide source. And it came down, some of it went onto the glacier here. Most of it went into the water. Some of it actually went down to a depth of around 90 meters out here and managed to climb up the other side of the fjord and leave a deposit that actually is on the land here and here. Really, really dramatic how dynamic this failure was. This photo is interesting also, taken just a few days after the landslide actually. This is one that was taken a few years after the 1967 landslide and tsunami in Gruink Lake. Again, you see the deposit on the ice here, but most of the landslide went in. This is actually a hummock, very similar to this one, that is protruding out of the lake. Both of these happen to be right at the toes of retreating glaciers. And there's a reason we might expect this is not a coincidence. We could actually, if you want to ask questions about this at the end, we could maybe dive into the details a little more, but very simply speaking, if you have a ice sitting in a valley like this, it is both eroding everything below the ice, so it's increasing the slope because it's not eroding the uplands, and it's also pressing out against the valley walls, so it's providing some support at the same time. And once that ice retreats, then you can have a mass fail like this. So here's a little trial for your satellite interpretation. I'll flip back and forth between these two photos from 2013 and 2016, showing Barry Arm in Prince William Sound, Alaska. And there's a lot of things that change. The glacier retreats, shadows change, the snow's a little different. But if you look just to the west, to the left of the B and Barry Arm, you'll notice there's a section of the mountain that actually translates enough that you can see this change on Landsat images. Yeah, when I saw, there's kind of a long story here. The really short story is when I saw this, my biggest contribution to the whole how this has progressed is that I was the one who really freaked out when I saw these. So, and really started raising some concern about this site. So this is a case where there does seem to be a remarkable coincidence between glacial retreat and landslide motions. This slope was actually moving long before the early 2000s, but it was during this pulse of rapid retreat that the landslide accelerated. And so that's kind of circumstantial evidence anyway that there's something going on. This is a cross-section I made for just kind of giving some sense of scale in a different way, estimating 174 meters thickness perpendicular to the slope of this mass. The reason why this particular site has become a big deal, so it's right here in Barry Arm, and this is Prince William Sound. So there's like places like you might have heard of, like Valdez, Cordova, Whittier here, and the preliminary modeling that's been done suggests that a wave here could actually be significant in this area. It could have some effects even out there, maybe even generate dangerous currents over by Cordova. And this area is actually heavily trafficked by vessels. So while these communities, have their particular level of risk, vessels, including vessels with hundreds, in some cases thousands of people on board, travel right up into these fjords, into the areas that were potentially badly impacted. So yeah, this is what that site looks like. I finally got to visit myself last summer, and I must say, like, you can't really see it if you're there. It's so big that you can't really take it in. So headscarp is somewhere way up here. Everything in this photo is moving. One of the things, there were a lot of things that came out of this, but one thing that in particular caught my attention is that this was really, really obvious. The fact that I can take two Landsat images, freely available, very low resolution, flip back and forth between them and see it, that is extraordinarily obvious geology. And there were actually people who were involved in the kind of initial framing of the response to this who had been in Barry Arm, geologists who sometimes work on landslide tsunamis, but were not thinking about this particular process, and they didn't notice it. And so one of the takeaways I had there was, well, maybe we should look around a little more. Maybe there are other things that we're missing. And this has been a big part of what I've been doing over the last few years. I'll just show one example of something I found here. This is an animation created by combining planet images. And you'll want to draw your eye to this area. So in July of 2020, this slow-moving landslide began, and it actually deflects the edge of the glacier. It's unusual that it looks so cool in like satellite time-lapse, but there is a lot going on. These are many of the sites that are currently in my inventory. This inventory is very ad hoc and non-systematic. It's not the one you want to do a bunch of statistics on. But I didn't include quite all of them in this version because there is a subset of these that are absolutely terrifying. These are the ones that, if we start, again, put our actuarial hat on, you might think these are worth, putting $100,000, $1 million worth of research into. And even if half of them ended up being no problem at all, that might well pay off in the end. However, right now there are very, very few of these that are being studied at all, and in many cases, the ones that are studied only minimally. So what does terrifying look like? This is the Maynard instability. If you've ever been to Whittier, Alaska, then you drove through a really long tunnel. This is the mountain that tunnel is in, and it has all these cracks. I'm just standing on it here. These are all bedrock cracks. If you look at it from more of a distance, it's pretty clear there's this large instability. We can see using satellite radar interferometry that it is moving, not real fast, fortunately, but moving centimeters per year. And it's in kind of the worst place I could imagine, in that if it failed, it would go into the head of Passage Canal. There's very deep water here, and Whittier is directly downrange in the areas where in other cases we see ridiculously high run-ups. This is a site that I'm working on with Noah Finnegan, who came up earlier in Columbia Fjord. So tour boats come up here all the time. In the summer, they're really busy, and they like to come right up in front of the ice. This ice is retreating an average of 2 meters per day, the ice front is, and it's currently, as we speak, pulling out from underneath the slope. Portage, this obvious instability, this is one of the most active ones in the state. It's moving centimeters per day often at the peak of summer. And it's above, if it fell down here, it's pretty easy for it to get to the lake. This lake has a big visitor center built on the shore. There are bridges and railways downstream. There's a tour boat that's out on it a lot. So these sorts of things, the hare is racing, right? No tortoise wins yet. This actually is Dennis Staley, if any of you know him, from the USGS. And he has kind of led the charge in really aggressive instrumentation and broad coordination to try to understand the Barry Arm instability back here. And also, we've been working closely together and kind of expanding that to look at other sites. And so there's a lot to hope for in that. If I come back to that silly tortoise and hare analogy, I wanted to point out a humongous flaw in that analogy. So I'm just for backdrop here. This is the village of city of Seward, and this is a big scarp because this mountain, Mount Marathon, very famous mountain, has shifted a bit in the past. Doesn't look very active, fortunately, but. So that analogy, there's the tortoise, the disaster, there's the hare, the scientist, but where is the community? Like, where is the people who are actually directly facing this hazard? So I'm going to tell a couple of stories that I think illustrate some ways that we leave that community out, or at least that there's a gap between the community and us, the physical scientists, trying to understand these hazards. And so in this first story, I am a community member. So I'm a part of the coastal peoples of Alaska, and in this case, I'm also a vessel operator, which I want to focus in particular on the community that operates vessels, whether you're native hunters or oil tanker drivers. Vessels do sometimes face tsunami hazards. So this is from the 1960 tsunami, very interesting case study. This one didn't make it, this tugboat. And it's pretty important for this particular hazard that we're talking about. This is the orange in here is all large ship traffic. So traffic of ships that actually use satellite tracking devices and that I can get a hold of. So it doesn't include a bunch of other vessels like that wouldn't be plotted in here. And they're traveling right out into the areas where these instabilities are. So if we look to the National Tsunami Warning Center for guidance for these vessel operators, I want to highlight a couple of specific points that they bring up. First, they say that you should go beyond the minimum offshore safe depth of 300 to 600 feet depth. And they also say that, reversing the order a little, your best option is to beach or dock your boat and get to high ground before the tsunami arrives. Now, I like this video because I can so easily put myself in the boots of these people in Nuugaatsiaq, Greenland in 2017 as the tsunami arrives in their village. And this is, growing up around boats you deal with stuff. Stuff goes wrong, and you need to react quickly and do what you can to rescue the situation. And so I can, anyway, I feel like I can read these people's minds. There's one piece that it's really hard to see because you're focused on what's going on in the foreground, but there's a boat out here. And so just for a moment, imagine that boat operator thinking about, should I run my boat ashore right now in order to flee to high ground, and be safe from the tsunami? In kind of wondering about this, I've actually done a lot of informal interviews of vessel operators. Every chance I get, anyone who uses any kind of vessel, I pin them down and I ask them what they would do. And all of them say they would go to deep water. None say they would run their boat aground. I'll wait a moment here. I think these guys make it. I mean, they published the video, so. But 4 people did die in this village, so it's and then the government of Greenland has evacuated this in another village, and I believe to this day they haven't allowed people to return. There are many, many reasons that I would argue that that's ridiculous advice. And when I talk to vessel operators, they all seem to agree. They seem to agree this is bad advice. Now, there is one little pewter lining to this story, and that's that none of the vessel operators I talk to have ever read the guidance. So maybe it's not a problem, but it isn't a solution either. So yeah, that's a story with me being a member of the community and calling out the scientific community on the weakness of what they're doing. Now I'm going to put on the scientist hat, and I think I look like a scientist here anyway. So when we first discovered Barry Arm, a bunch of us got together, a bunch of scientists, and we wrote a letter. There were press releases. It was a really very effective outreach effort. New York Times covered it immediately. However, none of us thought to get in touch with the local communities before it hit the New York Times. Many people in these communities that are directly threatened by this, they found out by reading the New York Times or something similar. And in hindsight, I'm like, what the heck were we thinking? That is ridiculous. It badly damaged trust, put up walls between us, the scientists, and those local communities. So that's an example where I had the other hat on and would gladly accept a big part of the blame. So yeah, I'm in some ways a scientist, and I look at these problems, and I haven't talked a lot about the gaps in our physical science understanding, but they're tremendous. They're hugely limiting in how we can respond to this hazard, and that worries me a lot. And I'm also somewhat a member of the coastal communities of Alaska. And I see these walls that I believe exist between the physical scientists and those communities that face these hazards. And that worries me tremendously too. I really, really worry that sometime, maybe very soon, maybe a little less soon, that this will be another tortoise story. I know I said I don't like that analogy, but I'm bringing it back anyway. That we are going to see something horrendous happen, and we'll have some ideas after the fact about how we might have not done so bad if we could go back in time and fix that. One of the things that we're trying in order to avoid this, we have this organization, it's very, very loose. I'm working on this with Anna Lillydahl of the Woodwell Climate Research Center, Arctic T-Slip. Anyone in here who wants to be part of it is welcome, totally open door. And so this organization is, it's a lot of scientists, but also quite a few community members, definitely still skewed scientists. And we meet about once a month, and we talk about what's going on, what's being learned. Sometimes there's presentations. We'll have a presentation on that new Gatsiak case on April 18th. And we're also pursuing funding in various ways. The one that we're really organizing as a whole group is around a large project support grant it's a new NSF model. And it may be something that's really designed to try to solve some of these problems, because very long arc where you work your way up before you really are pursuing the larger blocks of funding. And that process is supposed to be one where you build the community, both the scientific community and the stakeholder community, to actually address the problem. Now, I titled this talk Lessons of Cassandra, and so I want to actually touch on this Greek myth of Cassandra. And so Cassandra was a beautiful young woman, and Apollo really wanted to have sex with her. And so he thought maybe if I give her some really impressive godly gift, Apollo's a god, and then she'll have sex with me. So he gave her the gift of perfect foresight. She could see the future. She still didn't want to sleep with him. And so this made Apollo very angry, and he could not figure out how to take his gift back. So instead, he added on top of it a curse that she would never be believed. And so often when we think of the story of Cassandra, and I think especially if you're someone, if you're working in natural hazards, you feel a little bit like Cassandra. You really empathize with that. Hopefully you don't have all of her bad experiences. But that feeling of like, I know something bad's going to happen and no one's listening to me. So I think that's the natural analogy to draw in this crowd. But I want to for a moment empathize with Apollo. Apollo walked into this situation, and he tried to leverage the power dynamic. He really thought he knew what would be the best outcome in this relationship he had with with Cassandra, and he botched it. So I don't know. Maybe there's something to be learned there too. And I think maybe as we think about this, it's probably pretty clear to everyone that the Geohazards thread, while a strong one, you could have a lot of the same conversation about climate change in general. And this is a problem where these two intersect. But I think there's almost total overlap there. And this is a really, really tough problem. And I think that while we need to do really great physical science, we need to actually confront this. We don't have the luxury, I guess, of ignoring the issues that exist in this gap between stakeholder communities and the physical scientists. And so I know I'm far from alone in the idea of centering communities, centering indigenous communities in these kind of discussions. And I wanted to add a little wrinkle to that just before this, almost my last slide here, but just that I absolutely think that the conversation with indigenous communities is critical. And one of the things I want to see is us take what we're learning as we try to interact effectively with indigenous communities and apply that to other communities, whether it's vessel operators, it might be tourism businesses are a huge part of this in Alaska because they're the ones who are going really right into the most dangerous places. I even think about insurance companies as communities. It's a kind of terrifying one for me to think about. They scare me a lot. But I think we need to try to use these models and really understand more. So I will stop there. Just, I guess, to say, I really genuinely invite anyone who wants to join this, and I'd love to take any questions.